American chemist R.B. Woodward, now deceased, has to his credit 2 Nobel Prizes in chemistry. When Woodward was a graduate student, he figured out a set of rules that are today known as the Woodward-Fieser rules. Application of these rules allow one to determine the Lambda MAX for an organic compound. The predicted value is generally fairly accurate, within a few nanometers of the observed value. The rules work like this. There is a starting conjugated diene structure that a lambda value is assigned as a starting value. Based on the structure, the substituents, and so forth, increment values are added to this starting value. There are 2 groups that we'll consider: conjugated dienes and a conjugated enone system. Let's begin with the conjugated dienes. 2 double bonds, 2 carbon-carbon double bonds that are conjugated. Now there's 2 possibilities. Either so-called homoannular system, where the 2 double bonds, the 2 conjugated double bonds, are cis to each other and fixed into a ring. The other possibility is where the conjugated diene is open chain and not cyclic, as shown here, or it is a part of a ring system where the 2 conjugated double bonds are in a S-trans arrangement. If they're part of the ring, the 2 double bonds are not inside the same ring. They refer to this as a heteroannular system. If the system is a homoannular system, the 2 CC double bonds are part of the same ring, then the starting value is 253 nanometers. If it's acyclic or heteroannular, the starting value is 214 nanometers. Now, for every carbon-carbon double bond that's added to the starting system that's in conjugation with the 2 conjugated double bonds, one adds a value of 30 nanometers to the starting value, an increment of 30 nanometers. That's for both the homoannular and the heteroannular system. An alkyl substituent on one of the double bonded carbons, one adds 5 units. That's for both systems. If one has a so-called exocyclic double bond, one adds 5 additional nanometers. Now, an exocyclic double bond is a double bond that's external to a ring, what I'm showing right here. That is, this double bond are considered internal double bonds. This double bond with respect to this ring is external to the double bond, or we say exocyclic double bond. For every exocyclic double bond in the conjugated system, one adds 5 nanometers. Now, polar groups, certain polar groups will also have a certain increment that we add. If we have this kind of ester group, actually that doesn't change anything, and at 0, no change is made. If we have an ether type of group that's attached to any of the carbon-carbon double bonds in conjugation, we add 6 units. Again, that's for both systems. halogen atom, we add 5 units. A dialkyl amino group is a larger value, we add 60 units. Now, later we're going to do some examples to help clarify this. If we have a CC double bond conjugated with a carbon-oxygen double bond, then there is a different starting or base value. If one starts with a 6-membered ring or a non-cyclic parent system, the starting value is 250 nanometers. If it's a part of a 5-membered ring system, then the starting value is different, 202 nanometers. An enone that's not a part of a ring, an acyclic dienone, our starting value, our base value is 245 nanometers. Now, as in the case of conjugated dienes, every CC double bond that's added in conjugation, that extends a conjugation, we add 30 nanometer units. Now, alkyl substituents, or if they're part of a ring, we call that a ring residue. There's also increment values that we add, but they're different than what we saw with the conjugated diene. Now, let's start with this shorter system. We have the carbonyl-carbon. The carbon attached to that, the alkene carbon, is referred to as the alpha carbon. The next carbon over is called the beta carbon. If we have a longer chain of conjugation, we see that here on the right side of our diagram. We'll start out with the C double bond O. The carbon next to that, that's part of the conjugated system, is the alpha. Next carbon is the beta, then the gamma, then the delta, and so forth and so on. These are the letters of the Greek alphabet. Now, every alkyl or ring residue substituent that's attached to the alpha carbon is given an increment of 10 nanometers. It is, we add 10 nanometers to our starting base value. If we have an alkyl or ring residue substituent on the beta carbon, the increment that we add is different. It's 12 nanometers. If we have a alkyl or carbon residue on the gamma carbon, or the delta, or the epsilon, or larger, then we add 18 nanometers to the base value. Alright, we now go to the next slide, where we show a continuation of the empirical rules for enones. If we have polar groups, the increment that we add depends on the group and where it's located. A hydroxyl group, if it's at the alpha carbon, we add 35 units. If it's attached to the beta carbon, we add 30. If it's attached to the delta carbon, we add 50. This ester group, we add 6 units, no matter where it's attached. The methoxyl group, if it's at the alpha carbon, we add 35. If it's at the beta carbon, we add 30, and so forth. Chlorine, if it's at the alpha carbon, we add 15, and so forth and so on. Not going to go through all the values, but if they do arise, we can consult this table and determine the increment that we should add. As in the case of conjugated dienes, if we have an exocyclic double bond, we add 5 nanometer units. A homocyclic diene component, we add 39 units. Let's now look at some examples where we actually apply these rules. Alright, let's work this example. We note that we have an acyclic conjugated diene. Our table tells us that the base value for this is 214 nanometers. The next thing that will contribute are alkyl substituents. Along the conjugated chain here, we have no alkyl substituents at carbon 1 or carbon 2. There's just hydrogens attached. And we have one methyl attached at carbon 3, no alkyl at 4, and 1 at 5. Therefore, we'll add 5 for the one at 3, 5 for the one at 5, which gives us 5 plus 5, or 10 nanometer increment. And that's all. We'd have no polar substituents, no additional double bonds in conjugation, and no exocyclic double bonds. So the total will be 224 nanometers. Alright, let's do a second example. In this example, we have 3 rings fused together. So what we need to do is to find our starting conjugated diene system. We have these 2 double bonds as our starting system. These, you'll note, are 2 carbon-carbon double bonds that have a fixed trans relationship. These would correspond to the heteroannular diene system. The starting value, the base value for the heteroannular system is 214 nanometers, so that's our starting value. Alright, let's next look for carbon substituents. We have at carbon 1, this is the equivalent of a alkyl substituent. Since it's a part of a ring, it's called a ring residue. But it contributes the same as any alkyl substituent, namely 5 nanometers. So there's 5 for that. Carbon 2, we have this ring residue, and that contributes 5. Carbon 3, there is only a hydrogen. There's no alkyl substituents. Carbon 4 has 2 alkyl substituents, this methyl group and this ring residue. So there's 5 for the ring residue at number 2, 5 plus 5 for the 2 alkyl substituents at carbon 4. So the total is 5 plus 5 plus 5 plus 5, or 20 that we add. And now what else do we have? We have this double bond here, but that won't contribute anything because this third double bond is not conjugated with the other 2. It's isolated and separate. So there's no effect from it. If you look closely, we have one exocyclic double bond, that is, the carbon-carbon double bond between carbons 1 and 2 is external to the second ring. That pegs it as an exocyclic double bond, and we'll add 5 units for that. The other double bond between carbon 3 and 4 is internal to the second ring. It's not external to any ring. It's not an exocyclic double bond. So that should do it. We add up everything here. 5 and 4 are 9, 2 and 1 are 3, and then the 2. The predicted lambda max for this compound of example 2 is 239 nanometers. Alright, let's work a third example. In this example we have 3 rings that are fused. You can see that there are now 3 CC double bonds. They're all conjugated. From these we have to choose the diene which will represent the starting base structure. And we have 2 possibilities. We have these 2 double bonds. Those would be the heteroannular system, the double bonds that are locked into an S trans arrangement. And in ring B, we have a second possibility. We have these 2, which are homoannular, 2 double bonds locked in a ring into an S cis arrangement. Well, in a case like this, we want to choose the diene with the highest base value. The base value for these heteroannular double bonds is 214. The base value for the homoannular diene is 253. So the correct diene to choose as our base value is the 2 double bonds here in ring B, and that would be 253. Alright, 253 nanometers is our starting base value. We note that the double bond between carbons 5 and 6 is conjugated with our homoannular diene. That adds an additional 30 nanometers, so we'll add 30 to that. Alright, let's next look for exocyclic double bonds. We have one double bond that's an exocyclic double bond, namely double bond here between 5 and 6. It's external, it's exo to ring B, and that's worth 5 units. So we'll add 5 for that exocyclic double bond. Let's next look for carbon substituents on the conjugated carbon system. Start with carbon 6. We have one alkyl substituent. It's actually a ring residue. That's worth 5. Carbon 5 that has this carbon substituent. That's also a ring residue, so that would be 5 more. Carbon 4, there are no alkyl substituents, just the hydrogen here, so there's nothing to add. At carbon 3, we have a methyl substituent, so there's one alkyl substituent. That would be another 5 units. Then at carbon 2, we have this ring residue. That's an additional 5, note that. And then at carbon 1, we have 2 alkyl substituents, 2 ring residues here and here. Each one is worth 5. So if you count up all of the alkyl substituents, there are 1, 2, 3, 4, 5, 6. 6 times 5 is a total of 30 nanometers that we'll add. So 30 for the alkyl substituents, and let's add them all together. That's going to be 8, 6 and 5 are 11, carry 1, so that's a total of 318 nanometers. So our estimated lambda max for this molecule is 318 nanometers. All right, let's work a fourth example. In this molecule, as we examine the double bonds, we notice that we have a CC double bond conjugated with a CO double bond. That's referred to as an enone. And enones have designated base values. The two of importance are if the enone is a part of a six-membered ring or an acyclic system that is not a part of a ring, the base value, the starting value, is 215 nanometers. If the enone is part of a five-membered ring system, then the base value is 202 nanometers. And we note here that the enone is part of a six-membered ring. Therefore, our starting base value is 215. Nanometers. All right. Now, we note that the double bond between the gamma and delta carbons is conjugated with our starting enone system. That adds 30 nanometers, so we'll add 30 for that. CC double bond extending the chain of conjugation. Now let's look for exocyclic double bonds. Right here, notice the double bond between the alpha and beta carbons is exocyclic to ring B. So we will add 5 units for that. Now, let's look at the substituents. We have only alkyl substituents on the conjugated chain, and so let's begin. On the alpha carbon, we have only a hydrogen. There are no alkyl substituents. On the beta carbon, we have this alkyl substituent. This is a ring residue. Now recall that for an enone, the contributions from alkyl substituents have different values than for conjugated dienes. So this down here reminds us, this table, that a alkyl substituent on the beta carbon, we add 12 nanometers. So that will be 12 units for the beta substituent. On the gamma carbon, there is only hydrogen, there are no alkyl substituents. On the delta carbon, there are 2 alkyl substituents. We have the methyl group here, and we have the ring residue here. And our table tells us that for carbons that are gamma and higher, we add 18 nanometers. These carbon substituents are on the delta carbon higher than delta, so for each of these that's 18 and 18. Be the delta alkyl substituent. Alright, that should be everything. You don't want to always double check. The easiest mistake to make is to overlook something. Oh, by the way, notice the carbon substituent here is not considered, or the CC bond here is not considered a carbon substituent. That's a common mistake that people tend to make, so we're not going to add anything for that CC bond. Alright, so we just do the arithmetic, add the total, and it comes out to 298 nanometers. So the estimated lambda max for our compound in example 4 is 298 nanometers. Alright, let's do a fifth example. In our molecule here, we note that we have an enone system, CC double bond, conjugated with a carbonyl group. So we have to determine the base value to use. Basically, it'll be one of these two. It is a 5-membered ring system. That is, the enone is part of a 5-membered ring, and the base value, the starting value, is 202. 202 nanometers. Alright. We have no additional no additional double bonds in conjugation. Let's look for exocyclic double bonds, and the double bond between alpha beta carbons indeed is exocyclic, is external to our 6-membered ring here, and so that is a contribution of 5 nanometers. So we add 5. Alright. Let's now look at the substituents. We have a bromine substituent on the alpha carbon. I've listed here the entry shown in the previous chart. A bromine substituent in the alpha carbon of an enone system is worth 25. We add 25 nanometers to that. So add 25. That's alpha bromine. Okay. And now, what about alkyl substituents? There are, if you look at the beta carbon, there are 2 alkyl substituents here and here, both of them ring residues. And our table tells us that alkyl substituents on the beta carbon of an enone system contributes 12 nanometers. So you add 12 for each of these carbon residues. 12 plus 12. Beta alkyl group, beta alkyl group. Alright. And 2, 3, 4, 5, 1, 2, 3. That should do it. Now we do just add up the total here. And that's going to be 6 and 256 is the total for that compound, 256 nanometers.